happy to see you again for this session. For Chapter 9, we are going to cover uniprocessor scheduling. So when I say uniprocessor scheduling, we are focusing on a system where we have only one processor. So this is just a simple implementation, but this implementation can further reiterate for systems that perhaps have more than one processor. So for today, we are going to look at the scheduling objective, the criteria, and the policies and algorithm being used for uniprocessor scheduling. First of all, we are going to look at the objective of scheduling. Generally, we have scheduling on the system because we want to make sure that there are proper order on which processes execute. But specifically, the system objective on scheduling is first of all to have low response times. It means that it tries to respond as fast as possible. Secondly, we want to have high throughput, try to execute as many processes as possible. And thirdly, we want to have processor efficiency, whereby the processor will always have to do tasks whenever possible. So these are the objectives of the system when we have scheduling. By having high throughput, we also ensure that the processor is not idle and always doing a task during the time that every process is there waiting to be executed. So it means that the processor is doing the task either executing process or itself is actually doing the scheduling and picking up processes to be executed. If you remember, in our earlier chapter, we have so many types of process states, beginning from the ready, new, running, also block, suspend, and end of process. So how does these process states relate to the many existence of the long-term scheduling, medium-term scheduling, and short-term scheduling? For the fourth one, which is I/O scheduling, we already covered that during our previous chapter. So first of all, long-term scheduling or the job scheduler is the decision to add the pool of process to be executed. So usually when a user actually clicks on, let's say, an application icon, so it's up to the decision of the scheduler, in this case the long-term scheduler, to decide whether to actually allow that new process to be executed. So this decision to add new process to the already existing process in the process pool is the job of the long-term scheduler. So it decides whether a new process can actually be put into the queue to be executed along with other executing process. So this is the decision of the long-term scheduler. Next one is the medium-term scheduling. Remember that we have the states such as block and running or suspend and running. So the decision to whether a process needs to be suspended or running again or block and running again is the decision of the medium-term scheduling. It is to decide whether a process can be inside the memory or needs to be swapped out and go into the secondary memory. That is the decision by the medium-term scheduling. Next is the short-term scheduling. Now this is where all processes in the queue need to be picked on by the scheduler to be executed by the processor. Basically, the task of the short-term scheduling is to decide which process executes next. Lastly, among the four is the I/O scheduling. Basically, this is to decide which process gets to use an I/O based on the queue of whether a process has finished using a particular I/O devices. We have covered this in our previous chapter, so we will not cover this again in this chapter. So now I'm going to just explain further what is the relationship between those scheduling functions and the process state transition. Now, looking at this diagram, we have the new, suspend, ready, and running. So where is the role of of the long-term scheduling. Like I said earlier, the role of the long-term scheduling is to actually decide whether a new process can actually come into the system. Usually the decision is perhaps decided from whether we have enough memory to accommodate new processes, or there is enough slot in the waiting list to accommodate new process. So each time a long-term scheduling needs to decide is to decide whether a new process can actually comes in. So the more processes are created, the smaller the percentage of new process can comes in because we have limited resources. So this is the role of the long-term scheduling to pick or to decide whether new process can actually come in by actually weighing and justifying the existence of other readily available processes in the system. And then, apart from the long-term scheduling, we have the medium-term scheduling. If you remember, we have the swapping function to decide whether a process can stay in the main memory or need to be swapped out into the secondary memory. So this is the role of the medium-term scheduler, is to decide which process to be swapped in or out, or from out into in again, right? So the decision can be based on whether a process has been waiting too long and actually use the available memory that can be used for other processes. So it decide, okay, let's say process A is waiting too long, so now process B perhaps is coming in. So based on the decision from the medium-term scheduler, process A need to be swapped out and process B can come in. So this is the decision of the medium-term scheduler. So lastly, on the scheduling function comes the short-term scheduler. The short-term scheduler actually decided which process can be executed by the processor. So previously we have process that is actually ready to execute. Now the short-term scheduler will pick from all those processes currently waiting in the ready state, which one of it can be executed. So this is the decision of the short-term scheduler and also known as the dispatcher. So this one executes most frequently because usually we have so many processes waiting inside the memory to be executed. And the short-term scheduling is our focus of this chapter. So looking back at all the relationship between the scheduling function, this is how all those processes of scheduling related to one another. First of all, we have the long-term scheduling to decide whether to execute new process or not. And then we have medium-term scheduling to decide between the block and suspend and whether the process from the suspend state can be admitted again into the execution state. And then after that, we have the short-term scheduling to decide whether a process can actually run or perhaps block for a moment and decides whether the process needs to execute or wait in the ready queue for perhaps waiting for other process execution. So this decision you need to remember and understand how does each scheduling algorithm relate to one another, the long-term, the mid-term, and the short-term scheduling. Basically, the fundamental concept of scheduling is to try to minimize the queuing delay between waiting processes and try to optimize the performance in the queuing environment. This is to ensure that the process always have a task to do and the process actually don't have to wait too long before it gets executed. So for part 3, we are going to look at some of the method that's being used for short-term scheduler. Remember, the role of the short-term scheduler is to decide which process gets executed and after a while can be blocked again by giving way to other processes that needs to be executed. So this is the role of the short-term scheduler, and for this part, we are going to look at some of the algorithm being used for short-term scheduler. Generally, there are two categories of decision that needs to be made by the short-term scheduler, which is whether to use non-preemptive method or preemptive preemptive method. This actually specifies how does the scheduling algorithm will actually work. We will look at these two categories of short-term scheduler in the following section. So before that, let's look at the scheduling criteria for each of the method. First of all, you need to make sure that there is proper CPU utilization. The objective here is to ensure that the CPU or the processor here is as busy as possible. As busy as possible means that it will always do the task. It will not spend the time idling or waiting for another process to actually finish. The processor will always have something to do with regard to the process execution. Secondly is the throughput. We want to ensure that the number of processes that complete the execution per time is as many as possible. And then the turnaround time is the time to execute a particular process. Means that when the process executes, how long does it actually spend with the CPU before it finishes. And then the waiting time is the amount of time the process actually have to wait between the arrival and the execution time. And then lastly is the response time. This is the amount of time it takes from when a request was submitted until the first response is produced. This is not the output, but the response between the arrival and the response from the CPU. So we look at all of these criteria in the following example. So to differentiate between all those methods, we will look at this running example. So in this example, we have 5 different processes ranging from process A until E. So each process have different arrival time. For example, process A arrive at 0 millisecond, B arrive at 2 millisecond, C arrive at 4 millisecond, D arrive at 6, while E arrive at 8. And we have the service time. Service time simply means that how many time does a process require with the CPU. So let's say for A, it states that it requires 3 CPU time for it to actually finish, while process B requires 6 CPU time, and C requires 4, D requires 5, and E requires 2 times with the CPU. So we look at how does each of these process execute between different scheduling algorithm under the short-term scheduler. So before we go further, let's look at the difference between non-preemptive and preemptive method. Non-preemptive means that once a process has already running, it will continue to run until it finishes all the required time with the CPU. So let's say a process requires 3 CPU time, so it will actually spend 3 CPU time with the CPU until it finishes, and all other process needs to wait until all those 3 slots with the CPU actually finishes. While the preemptive method is that there are sort of the preemption or a instance where the process will be required to stop execution if, let's say, a new process arrive and interrupt, or they have a queuing mechanism based on the clock interrupt. So we will look at the difference between non-preemptive and the preemptive method to see the differences. So try to understand each difference between the non-preemptive and the preemptive method in the following example. So let's look at the non-preemptive policies first. Now, the first method is the first come, first serve method. So this basically is the simplest form of scheduling policy. It simply means that once a process arrives, it will continue to execute until finishes, then only the next process can execute. So for example, let's look back at the diagram here. So we have process A, B, C, D, E. So how do you actually do this diagram simulation is you need to actually draw. Okay, let's see how much time slot that you need to actually draw. So let's say you need to actually add all this service time. So let's say 3 plus 6 plus 4 plus 5 plus 2, it will constitute, let's say, for about 20 milliseconds. Okay, so you total it up, then you just draw this line until it constitutes all the total time slot for all the process to actually finishes. And then for this axis, you put all the process name. So in this example, we have process A until E. So next, how do you actually accommodate it into the diagram? So we see here, okay, the service time for process A is 3. So you take 3 blocks from this diagram and put it for process A. So 1, 2, and 3. So this one is the execution time for process A. Next, for process B. So process B requires 6 service time with the CPU. So you use 1, 2, 3, 4, 5, 6 for process B. The next following one is process C. Okay, process C requires 4 service time with the CPU. So you have here 1, 2, 3, 4 service time with the CPU. Following that, we have D, 5 service time. And then lastly, process E, 2 service time. Alright, so the execution method for the first come first serve method is that each time a process arrives, it gets the priority to execute, okay, because it is first to arrive. So in this case, A gets the first priority because A arrived first. So A execute until finishes, and then B execute until finishes, and then C execute until finishes, D execute until finishes, and E execute until finishes. So this is a non-preemptive method. It's a very straightforward, but there is the downside. So we will look at the downside later on. What is the downside? Look at the next following slide. Now we need to actually calculate the average waiting time for each of the process. We want to see how long does an average process needs to wait before it actually gets to execute. So remember we have the arrival time before. So this is where we use to calculate the waiting time. So remember for process A, the arrival time is 0 and immediately it gets executed. Okay, 3 slots in the CPU. And then we have process B. The arrival time is 2. So B arrived here. Okay, so B arrived here and then it gets executed at the third millisecond. So you see that there is a gap here before it gets executed. So the waiting time for process B is actually 1. And then during the execution of process B, C arrived. So C arrived here at the 4th millisecond. So here, remember, the arrival time for C is 4. So 4 is here. This is the arrival time for process C. So before getting to execute, it needs to wait for process B to finish all these slots with the CPU. So it finishes at the 9th millisecond. So you need to calculate between this and this, how long does C has to wait. So this is where you get 9 minus 4, you get 5. Or you can just straight away count between this block. C arrive here, it executes here. So 1, 2, 3, 4, 5. So the waiting time for C between the arrival and the execution is actually 5. Okay, next is the arrival of D. So D, the arrival time for D is 6. So D arrived here. Okay, so between the execution of D, it needs to also give way to C. So C is executing here 1, 2, 3, 4 until here. So you see at the 13 millisecond. So D from here, it only gets executed here. So how many blocks are there? So you can calculate this 13 minus 6, the arrival time of D, then you will get 7. So the waiting time for D here is 7. And then we look for E. So for E, the arrival time is 8 here. Here, E arrived. So it needs to wait for the execution of D before it actually gets the time for execution. So the arrival time for E is 8, but it gets executed at the 18 millisecond. So 18 minus 8, you will get 10. Or you simply count the number of blank in between the arrival and the execution time for process E. So how to calculate the average waiting time? This is where you total up all the waiting time here, 0 plus 1 plus 5 plus 7 plus 10 divided by the number of process. In this case, we have 5 processes total. So you total up all the waiting time divided by 5 and you will get this value, 4.6 millisecond. So this is the average waiting time being used for the first come first serve method. Okay, try to understand how this calculation is being done, then we continue to the next part. Okay, so based on this example, the first come first serve method performs much better for long processes, because let's say even a process is short, because it arrived late, it needs to actually wait because it arrived so much later in the queue. So although it takes just a short while to execute, but it needs to give way for all the previously arrived process in the queue. So whether the process is short or whether a process is long, it is being treated based on the arrival time of the process. So this one, let's say the process is so much smaller to execute, but it needs to wait such a long time before it gets the proper time to execute. So it does not really favor short process because it just do the decision based on the arrival time of the process. So next, because we have the problem with the first come first serve method, now we have another implementation in the non-preemptive method, which is the shortest process next. So we want to see whether if let's say we make the decision differently from before. This is to decide between the process, which one is the shortest, then we pick the shortest process first. So how does this fare in the comparison? So in this case, we are going to look at the next example. So how is the decision being made if let's say it is made based on the service time required by the processes? Will it perform better or not? So how does shortest process next work? Basically, let's say you have more than one processes waiting. Okay, so in the first few rounds, there will be no difference between first come first serve because there are no competing processes. So for A arrived at 0. So of course A arrived and it gets executed immediately because there are no competition. So A execute, and then during execution of A, B arrived. So B arrived during the second millisecond. So after that, after A finishes, immediately B execute because naturally no competition also from A because A already execute. Now B needs to execute next. So after that, during the third millisecond, B execute. Now, this is where it gets interesting. So during the execution of B, so you see that we have the arrival of C, the arrival of D, and the arrival of E. So this is where the decision making process takes place. So if there are competing processes, the decision of which process execute first is decided between the processes there. Which process is the shortest? So between these three processes, C, D, and E, it compare the processing time. So E is 2, D is 5, C is 4. Of course, based on the comparison, E gets to pick as the next process to execute after B finishes. So after B finishes, E execute. Now, after E execute, next decision is between D and C. So between D and C, which one is the shortest? Of course, between D and C, C is the shortest. So C gets executed next. And lastly, only D will execute because there are no more waiting process. So the key here is, in order to decide which process execute next, is decided based on the service time. So the process with the shortest service time will pick to be executed. So how do we calculate the waiting time? Still the same. So A arrive at 0, immediately execute. So the waiting time for A is 0. B arrive at the second millisecond and gets executed during the third millisecond. So the waiting time is 1. And then C arrive at the 4th millisecond, gets executed at the 11th millisecond. So the difference is 7 millisecond of waiting time. And then D arrive at 6 millisecond, gets executed at the 15th millisecond. So the waiting time is 9. While E arrive at the 8th millisecond, gets executed at the 9th millisecond. So the waiting time for E is 1. Then we calculate the total waiting time and the number of process. We get the average waiting time. So 1 plus 7 plus 9 plus 1 and divided by 5, we get 3.6 milliseconds. So a bit faster from how first come, first serve actually perform. So of course, this is very important if, let's say, short process is a lot in the burst of the arrival process. So it will pick the decision based on which process is the shortest, then that process gets executed first. Okay, if there are competing process, it will pick the shortest process and pick that process to be executed first in the queue. The next algorithm is the highest response ratio next. So how is it actually different from the shortest process next and first come first serve? For one, it actually chooses the process based on the ratio of the age of the process with the time that the process actually gets executed. So the formula here used is that it based the ratio based on the time that it will spend waiting plus the expected service time required by the process and the expected service time. Now, for the following slide, we are going to look at how we actually do the comparison and choosing the next process to execute. Right? So the same just like before, for process A and B, there is no competition among the process. So once A arrives, only A is there in the waiting. So A immediately gets executed. So after A finishes, B gets executed. And also note that during execution of A, only B arrived. So no competition there. So no further calculation is needed up to this point. Okay, so we will look at it once C, D, and E arrive next. So what will happen and how to do the calculation. So after B is executed, you will take note that there is the arrival of 3 processes. So we have the arrival of C, D, and E. C arrived at 4 milliseconds, D arrived at 6, E arrived at 8. So we need to calculate between those 3 processes which one have the highest ratio. Okay, so we look here. C arrived at 4, D arrived at 6, E arrived at 8. So how to do the calculation? First of all, we estimate, okay, at this millisecond, the 9th millisecond, each of this process need to actually be peaked. So the value of 9 here will be the baseline for the number here to count the ratio. So 9 minus 4, which is the arrival time, plus 4, which is the service time, divided by 4, which is the service time. So 9 minus 4 plus 4 divided by 4 is 2.25. And then for D, this ratio 9 minus 6, which is the arrival time for D, plus 5, which is the service time for D, divided by 5, which is the service time for D. And we get this number 1.6. And then for E, 9 minus 8, the arrival time for E, plus 2, which is the service time for E, divided by 2. Then you will get this number. So between 2.25, 1.6, and 1.5, which process will get picked for the next in line for execution? So of course the answer is C will get picked next. Okay, so C is chosen here. C is chosen because it has the highest ratio here, 2.25. So based on the calculation, C has the highest ratio, hence C gets to be picked. So the next decision is which process between D and E to be picked next. So can you guess? Try to do the calculation before moving on to the next slide. Now, for process D and E next, the calculation will start considering that during the 13th millisecond, it will need to decide whether D or E will execute. So the real calculation you need to do from the 13 millisecond. 13 minus 6, which is the arrival time, plus 5, which is the service time, divided by 5. Then you will get 2.4. And then for E, also the same. Begin from 13 minus 8, okay, which is the arrival time for E, plus 2, which is the service time, divided by 2. Then you will get 3.5. So based on these two ratio, which one will get picked? Of course, the one that will get picked is process E because E has the highest ratio between E and D. So E is chosen, E gets executed. And after that, of course, D will get chosen because only D is left. And after that, same just like before, you need to calculate the average waiting time for the process. So again, you do the calculation for the waiting time, which is the arrival time of the process, and compare it with the actual time the process gets service. So you will get this number 1, 5, 9, and 5 divided by 5. So we will get the 4 millisecond value. So between process HRRN, highest response ratio, and the shortest process next, and the first come first serve, we see that the HRRN here performs slightly better than first come first serve. But in comparison among the three, the shortest process next perform the best. So now we look at the preemptive policies. So before we continue to this part, please take a moment to rest and perhaps review what we have learned so far, which is the non-preemptive method. Once you understand those methods, feel free to continue to the next part on the preemptive policies. First, for the preemptive algorithm, we are going to look at the shortest remaining time. Okay, so you need to remember for preemptive method, it means that every time a process executes, it has a chance to be interrupted. So the interruption can be caused from the arrival of new process or perhaps based on the time quantum given to a process for it to execute. So for shortest remaining time, we look at this example whereby each time a process executes and after arrival of a new process, it needs to make a decision based on the shortest remaining time for the process. So how it will actually do that? We look for the next slide for the explanation on the method. In terms of execution, we need to look at how does it do the comparison. So in this example, for preemptive method, it will make the comparison each time after a slice of execution has been done. So in this example, let's say again, A execute for the first time, alright, up to here, no competition because no other process has arrived yet. After the second execution, B arrived. So at this point, the remaining time for service of A remain 1, while the remaining time for B, here you can see that the remaining time for B is 6. Okay, so after that, we see that it needs to decide between B and A, okay, because A has 1 and B has 6, so A is chosen. Now, after A has finished, of course, no competition, so B execute. Okay, but after one quantum of time of execute, okay, we see that C arrive. Okay, B only success executing only one cycle, then C arrive. So up to this point, it needs to compare between the C and B service time. So upon arrival, the remaining time for C is 4, while the remaining time for B is 5. Okay, between 4 and 5, of course, 4 is smaller, so C gets the priority to execute. So C execute one slice, and then after one slice of execution, it needs to compare between C and B because at this time, only two processes is there to compare. So C and B, now C already finished one slice of execution. So the remaining time for C is 3 and the remaining time for B is still 5. So between 3 and 5, of course, C is smaller, so C execute one more slice. So the remaining time for C up to this point is 2, while the remaining time for B is still 5, and then up to that point, D arrive. So now we need to compare between three processes, D, C, and B. So the remaining time for D is 5, remaining time for C is 2, while the remaining time for B is 5. So between D, B, and C, C is still the shortest, so C gets the priority again to execute. And then also up to this point, C is also the smallest, C gets to execute again. Then comes E. So now we need to compare between E, B, and D. So between E, B, and D, which one is the shortest? Of course, E has the shortest remaining time, which is 2, while D has 5 and also B has 5. So after execute one slice, again, we need to compare again E, B, and D. E, B, and D, between them, E remains the shortest remaining time while B still has 5, D still has 5. So E finishes execution. And then again, we remain with B and D. So between B and D, both have the same remaining time up to this point. B has 5, D has 5. Okay, so at this point, because B arrived first, so B gets to execute first one slide. So one slice of execution, after that we compare between B and D again. So of course, after one execution, now D remains 5, while B now remains 4. Of course, B is the shortest, so B gets to execute again. And when compared, of course, up to this point, remaining time for B is 3, remaining time for D is 5. Again, B gets to execute, and also execute until it finishes, because the remaining time will continue to be smaller and smaller because no other process are in competition at this point forward. So B gets to finish, then the time has arrived for D to actually execute one by one by one by one until finish. Okay, so again, how to calculate the average waiting time is to compare the arrival and also the execution time. So for the execution time here, okay, let's say for A, no waiting time. For B, there is one waiting time here, and also the waiting time in between here, 1, 2, 3, 4, 5, 6. So in total, the waiting time for B is 7. Okay, and then for C, there is no waiting time because up to this point of arrival, C always execute. And then for D, the execution time is from this point up to this point. So you get 9. And then the execution time for E is 0 because it executes immediately upon the arrival. So you add up all the total divided by 5 and you get 3.2 milliseconds. So this is the performance of the average waiting time for the shortest remaining time algorithm. Okay, if you don't get it, please repeat back my explanation and perhaps you can get a much more clearer description of how this works. Another method in the preemptive approach is the round robin. So what does round robin do? Basically, if previously we have the interruption and checking whether the remaining time is actually shorter or longer than the other process, round robin this time has an interruption based on the quantum size. So for example, let's say the quantum size is 1. So each time a process execute one time, it will actually stop and have to wait in the ready queue, and the interrupt process will actually execute. And this continue until all the other process actually arrive, interrupt, and needs to execute. So for the following slide, we are going to look at the same example, but this time according to the round robin with a quantum of 1 time slice. So in this example, I have color-coded each of the process with different colors. So for A, there is green, B, orange, C, blue, D, red, and E, yellow. So it's still the same process and the same arrival time and the same service time. The only difference is that this time, each process is only allowed to execute one time, okay, if it's not actually interrupted by the other process. So here we have process A until E and the arrival time of each of the process. A arrive at 0, B arrive at 2, C arrive at 4, D arrive at 6, E arrive at E. Okay, so we will look at it how it's executed based on the round robin method. So for the first time, okay, you need to make two queue. There are running queue and also there are the ready queue. So each time a process is running, it will be using the running queue, and if it needs to wait, it will use the ready queue. Okay, so for the first time, okay, A arrive, okay, then A execute, and after that A execute again because there are no process interrupting A. So here on the diagram you can see that A execute for 2 time slice before the arrival of B. And then next B interrupts A because B actually arrived in the queue, then it interrupts A's execution. So because A was interrupted, A is moved into the ready queue. Okay, so A waits in here. So what happens next? Okay, B execute because it has interrupted A and A needs to wait. Okay, see here in the diagram. Okay, B interrupts A, so here is B interrupting A, so B gets to execute, and A now waits in the queue. So for the next one, okay, A interrupts B again, because you remember for round robin, each process only gets to execute one slice of time. So after B interrupts A and B execute, and after that it is A's turn to execute, so A will interrupt B. So the rule here is that any process that is waiting in the ready queue will be the one that will be interrupting next. So previously A was waiting here. Now for the next cycle, A will interrupt B. Okay, this one is B's execution, and after one slice, A will interrupt B again. Okay, so once interrupted, B will need to stop and wait in the ready queue. So B waits here, A now gets to execute. Okay, so A execute, B waits in the queue. Now C arrive. Okay, so when C arrive, C is waiting inside the ready queue. And then the next time, okay, if you notice here, okay, A has already executed all its service time, 1, 2, and 3 here. So A is out of the competition now. So A has already serviced 3 times. So now it's between B and C. So previously B waits in the queue because A was executing and C arrived. So next one, after A has finished, so now A has finished all its service time 3 times. Now B is getting out of the ready queue and now is running. Okay, C is arrived here. So you need to cross out B here, and the next in line will be C during B's execution. So B is running. Okay, here B is running, and then C interrupts B. Okay, remember any process that is previously was ready, it will interrupt the running process after one slice of execution. So previously B was executing, now C getting out from the ready queue, C will interrupt B. Okay, so once C interrupts B, what's next is B waits in the queue again. So here it will go on until one slice, it will check who is interrupting who. So B waits in the queue, okay, and C is executing there. Then D arrive. Okay, this is arrival time of D. So what do you think happened next? So D arrive here, D is waiting in the ready queue, and C is executing. Okay, so next, who will be interrupting who? Will it be B or D? So the answer is B will interrupt C, because in the queue, B is the first in line followed by D. So logically, B will interrupt C, the one that is executing. Okay, so B interrupts C, and of course C needs to wait in the queue. Now B is running. So next, who will be interrupting who? Okay, B execute. Now who will be interrupting B? The one that will be interrupting B is of course D, because previously D was waiting here. Okay, D is still waiting in the ready queue, and B execute, and C is waiting. Now previously D was waiting. Now D needs to get out, so D interrupts B. Okay, so D interrupts B, so D will execute here in the red. Okay, so next one, E arrive. After one slice of D's execution, E arrive here. Here. Okay. So where will be E waiting? So E will be waiting after B is interrupted here. D interrupts B. B waits in the queue. E arrive. So now there are three processes there. So D is executing here. Okay, there are also processes waiting previously in the ready queue. So next, C will interrupt D. Okay, the process that was interrupted will go into the ready queue. Okay, and then it will follow this flow on and on until all the processes finish executing according to the service time here. Okay, so now C interrupts D, D waits in the queue, and after that, who will be interrupted during C's execution? Who have not yet interrupt anything? Okay, so you need to actually cross out any process that was interrupting other process later on. So after C interrupts D, D waits in the queue. Next is B interrupts C. Okay, C waits in the queue. Okay, B execute, C waits in the queue, and then E interrupts B. Okay, so E execute here after it interrupts B, and B waits in the queue. Okay, and then it's time for D, and then so on until the process continue until finishes. Okay, so the round robin here that you need to remember is that each process is given one slice of execution before it can be interrupted. So any process after that one cycle will interrupt the other process. So who is interrupting who is decided by which process is previously waiting in the ready queue. So any process that is running will be interrupted by the process in the ready queue. So if it's hard for you to follow this one, okay, you can still repeat it for my side of the explanation and see whether you can understand how round robin works. Okay, so any process will then execute until finish, okay, until it has no competition at all. So it will need to execute according to the service time that is stated here. So as you can see, A still execute 3 times, B execute 6 times, C 4, D 5, and E 2. Okay, so the process continue until all the required service time is actually serviced by the CPU. So again, in order for you to calculate what is the waiting time and the average waiting time, is you count all the time that is required for the process to wait at the end of the cycle. So here, A is required to wait 1 time here, and B required to wait from here until here. So you see the empty blocks there. This is the waiting time for the process. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is for B. And for C, okay, the arrival time for C is 4. So here, so there will be empty block here. 1, 2, 3, 4, 5, 6, 7, 8, 9. That is the waiting time for C. And then D arrived at 6. So it arrived here. And the waiting time here is 1, 2, 3, 4, 5, 6, 7, 8, 9. That is the waiting time for D. While E arrived at 8. So it's here. 8. So it execute and it needs to wait 1, 2, 3, 4, 5. So the waiting time for E is 5. So the average waiting time you total up all the waiting time for the process and divide it by 5, and you will get this total. So the average waiting time in this sense for the round robin is 6.8 milliseconds. So this is the performance of the waiting time if it uses round robin. For this chapter, you need to remember the difference between the long-term, medium-term, and short-term scheduling. Each of those scheduling methods has a purpose in the system. For example, long-term will decide whether a new process can go in and start in the system, while medium-term will decide whether a process can be swapped in or swapped out from the main memory. And lastly, short-term decides which process can actually run after it is being blocked or suspended. So, the focus of this chapter also is for you to differentiate between the many methods of short-term scheduling which involve the category of preemptive and non-preemptive method. So differentiate between the two non-preemptive and preemptive method and see how does those approach perform in terms of the average waiting time of a process. Okay, so I hope you can remember all those thing of how scheduling work and what is the purpose that we have scheduling. Okay, so you can remember and try to appreciate how does operating system actually does this for a very constant time to make sure that the process need to execute whenever it enters into a system. So for the next session, okay, I hope this can be used to further understand and appreciate how does operating system works. For chapter 12, we are going to talk about file management. Basically, files are being used after, let's say, certain data has been processed and we need to store it somewhere to ensure that we can get back for our work whenever we want to do it again, or perhaps we want to save the data that we have processed. So for this chapter, we are going to look at the file function, access rights, and file allocation method. So first of all, let's look at the file system and structure. Basically, the structure of a file enables for us to actually store information for it for the long run. So let's say after we process any data or information, we need to have assurance that those files will be available again next time we want to use it. Also, we want to make sure that those files can be shared between processes, and also each of these files have a very unique structure and metadata with regard to the information that is stored. For example, the system will be able to recognize what data does the file represent, which process actually uses it, and which program can be used to open the selected file for it to be able to be shared between processes and perhaps between I/O devices. That is the main aim or the desirable properties of file. We want to ensure that it exists for a very long time, it is shareable, and it has a very unique data structure or metadata that can be easily identified or linked to a unique file or process that use it. Also, modern operating system enables these 6 operations or functions to be performed on a file. These actually the things that you usually do on a file. Basically, if you have a file, you want to make sure that you will be able to create, delete, open, close, read, and write the file according to the requirement of the process. So these are the basic operation or function that you want to perform on a file. And when talking about file, we almost certainly will link file to the directories attribute. Basically, this information about the files are contained in the directory. Usually, in the directory, we have information such as the attributes, which is the size, format, and creation date of a file, the location of the file, which is where is it location on the disk drive, and the ownership, who has written the file, who is the creator and owner of the file. And also, you need to remember the directory itself is also a file owned and managed by the operating system. It provides the mapping between the file names and the file themselves. Remember, when you open File Explorer, for example, you will see that inside the directory, or also known as the folder, you can see all related information on the branches of the file that is contained in the directory. It enables the user to easily locate files and find information with regard to the file that they are using or looking for. So having a proper directory system enables the user and also at the same time enables the operating system to easily manage this file that perhaps the process wants to use or it wants to use by the other I/O devices. So apart from other operations that can be performed on a file, when having a directory, you can also have this function. You will be able to search, create file, delete file, list the content of the directory, and also update the directory information. These are other functions on top of the previous function that you can perform on a file. Also, each file that you use has a certain structure to it. Usually, you will also use this type of file structure without you even notice it. Usually, there are four terms that is commonly used when discussing files. First of all, there are field, record, file, and database. Perhaps this term is also familiar to you, but perhaps this is a refresher for you to understand what is the difference between field, record, file, and database. So we start from the very basic component of a file structure, which is the field. Remember, when you are actually entering your information in a page or perhaps in a form that you fill in the website or each time you register for an account. So for example, these are the field. So the field contains the basic element of data, contains a single value, let's say your name, address, or perhaps your user ID. That is a field of data. After that, if you have a compilation of those fields of data, so you have a record. For example, your student record contains fields such as your student ID, your name, and perhaps your address. So those collection of fields will constitute to the record. And let's say after you collected those records for one student, let's say you have 10 students record, so you have a file which is the collection of similar record, and then from that collection you have the database, which is the collection of related data. So let's say you have a collection file of user or student information, and at the other database you have the collection of perhaps the student grades. So this constitute the database of student records. So still to differentiate between this data structure from the field, the record, the file, and the database. The reason we have this structure is because for us to enable easy finding and navigating for those files if let's say we want to use the information to perhaps data processing and getting certain result or analysis from those databases. And in order to manage the file, the OS have this capability of having the file management system. So the objective of the file management system is basically to help the OS in order to fulfill the data requirement or the data management needs of the user. It also have a record checking capability to ensure that the data in the file are valid and optimized to ensure that there are no duplicate of data, to ensure they have proper I/O support for a variety of storage data type, and to minimize potential of loss by providing usually backup of those data and a standardized set of I/O interface to enable for the user to easily identify this data can actually be used for what type of application. And lastly, it to provide the I/O support for multiple users in the case of multiple user system. So basically, every modern operating system have this FMS capability to enable for the user to easily collect data and also compile the data and perhaps use the data as they see fit according to the needs of the application. So let's say sometimes you have a collection of student record and at the same time you have a collection of student result. So you want to use the data to see which student actually perform better and which student actually requires more help with the system. So this capability is being handled by the operating system so that you easily or have a certain support and backup in case you want to use the data again in the future. So in order to have a proper FMS, the system must have the very delicate software organization for files in the system. Basically, the typical software organization for file management is considered part of the operating system. So in here, it has the structure of the user program up until the use of the I/O devices to store those files. So let's say you have a user program. So each of the user program has a certain way to collect the user data, and this data will need to actually be or having proper permission before it can be used by the process that requested it. So we have the logical I/O, which give the user a very standardized and easy to understand structure of the file inside the system. And you have the I/O supervisor, which supervise whether a process can use a selected data from a file. And we have the disk device driver to ensure that, let's say after you save the data or want to use the process later on, it needs to understand where does the data come from and where do you want to save the data after you actually process it. Also, we have the start data structure in the basic file system, which enable the directory to be made and structured for that it can represent information for the user to easily find it and obtain whatever related information with related to the file, such as the owner, the format of the data, the application that can use it, and so on. So this structure, okay, must be managed by the operating system to ensure that whenever a process is using a file or is saved into a file, it can easily be recovered later on when the user needs it. That's why this typical software organization for a file is part of the operating system. Of course, when we talk about file usage, we must also consider the file sharing and access rights that can be given to a file owned by the user or the system. So this needs to be considered, of course, when you have a multiple or multi-user system or you have the data that can be shared by multiple users. So the system must be able to have this mechanism of having proper access right and also managing multiple user access to the same file or data. So basically, these are examples of the access rights that you typically see on a file system. For example, let's say you own a file in your Google Drive or perhaps in your uh, or share file or folder. So you have this access right or you can give the access right to the trusted people that you want to share your file with. Usually, for example, for the basic one is you have the non-access right. It means that the user will not be allowed to even see the file inside the directory. And after that, let's say you trust this person and you want to make sure that they can see that file but they cannot use anything else. So you give the knowledge access right, followed by execution where the other user can actually execute the file inside the directory and read the content of the file, append meaning add information to the file, update the information to the file, changing the protection if you are the owner of the file, and also delete the file if let's say you are the owner of the file. So these are the type of access rights usually can be managed by the user or the owner of the file or even the operating system if it's given proper management rights. The purpose of having the access right is to protect the file from being misused, and the management of these files are usually given to the user as the owner of the file. So the owner will decide what can be done to the file and who can actually share the access to the file that they own with. When we talk about also the access side, there are this grouping of the specific user group. So for example, as the owner, so usually the class owner is the file creator, and he or she has full rights and may grant this right to others. And usually this grant of access usually is given to the specific group where you trust, or perhaps in your work group, or perhaps your organization. And also sometimes you can also give the access to a certain user group. Let's say student access group is capable of accessing this type of information, while the admin can access other types of file privilege. And let's say the file is not very private or confidential, so you can give the access to all users. So these user access rights and classification are ways that the OS is given privilege to the user to easily set up how information or data can be shared from the file that is owned by the user. Because files are being stored on the secondary storage, which is your hard disk, so we are going to look at the secondary storage management for files, which is the use of the FAT. Usually, you always heard this, or you need to format your storage according to the FAT format, or nowadays we have the exFAT format. So basically, what is the FAT? Basically, on the secondary storage, we have the blocks of memory. Just like you have a blocks of memory in the main memory, in the secondary memory is also the same thing. Files is stored in blocks. So this allocation of blocks that can be used for files are given to the files whenever it needs to be stored on the secondary storage. And as always, usually, ideally, files are scattered all over this allocation inside the hard disk, because the available space that you have on the hard disk is also the situation is kind of the same, just like when you have in the main memory. You usually have these available blocks scattered randomly according to the available blocks. So how does OS actually tie these empty blocks together for it to actually store information or files that is perhaps usually in succession or in continuous block of memory? So in order to solve this problem came the FAT, or the file allocation table. So simply put, the file allocation table is the data structure that is being used for the operating system to keep track of the portion assigned to a file. Just as you know, for example, you cannot ideally have a continuous block that can be used for files. So in order to reference this link of files that is scattered all over your hard disk, it needs to have a proper database or data structure to keep that information. Let's say block A, block Z, block Y, and block X, for example, is being used to save file A, while perhaps block 11, block 11, block A, and so on is being used by process B. So you need to have a proper bookkeeping mechanism, which is in this example is the file allocation table, to keep tabs on all the link which actually being used by the file when it is being stored. And in order to allocate this required space that is being used or might be used for file, there are two problems. First of all, either to use pre-allocation policy, it means that any file that needs to be created must declare in advance the amount of space or megabyte that it will be using, or perhaps dynamic allocation, which needs to allocate the file size according to the current need of the file. So each of these have their own downside. First of all, pre-allocation, of course, you will not know in advance how much space you will actually use. While dynamic allocation, you need to always constantly check for the available space that can be given to a file according to its use. So for the second one, dynamic allocation, of course, it needs more help from the processor because it needs to constantly check the availability of files, while pre-allocation policy might contribute to the wastage of space if it's not fully utilized. So these are the usual dilemma whether to use pre-allocation or dynamic allocation. The next consideration is also considering the portion or basically the block size that can be used for files. So let's say for first approach you want to use contiguity of space, means that let's say you have 8 blocks of 2 megabyte each that can be used for a file in a continuous manner, or you want to have a large number of small portion and increases the size of tables needed to reference this file later. So this consideration of the portion or the block size also needs to be considered by the operating system to ensure that the block size are optimally used when the files are being saved into the secondary memory. So either to have a continuous space that can be used for files, or you can have a small portion of blocks of memory that can be used for files later on according to the needs. So from that, two major alternatives are being considered. First of all, whether to have variable large contiguous portion or dynamic allocation but in a continuous form, and it is given according to the needs of the file, or you can have a size block which is, let's say, 8 megabytes for file A and 8 megabytes also for file B, for example, is given according to the pre-allocation policy based on the estimated needs that perhaps the file will need. So either use variable or continuous portion, or you want to use block. So these are the consideration that can be used to store file in the secondary memory. So how is it used? We will see in the next section. For the first approach, which is the contiguous file allocation, this one is allocated to a file during the time of file creation. So this file pre-allocation strategy using variable size portion and according to the estimated needs of the file. So let's say it is estimated for file A here, it will need to use 3 blocks of memory, while file B, it needs to use about 5 blocks of memory, while file C, 8 blocks, and so on until file E. So usually how is it done is each time a file is being created, it needs to give some estimation of how many blocks that it will use. So from that information, the OS actually gather the appropriate size that can be given to a file according to the pre-allocation determination of how much block that can be used to a file. So after the space is given and the space is populated by the allocated process, from time to time, the system will perform a compaction algorithm to free up additional space so that it can be properly managed and given to the next file that will perhaps use the memory space. The next method is using chain allocation method. So previously we have a continuous flow of file block that can be used inside the secondary memory. Now in chain allocation, The allocation can be randomly allocated across the memory block, but it is chained together and is collected in the file allocation table. So let's say in the file allocation table, it will state that the file B is constituting of this block of files. So when it needs to form back the file, the allocation table will give the information of which block actually form the file. So each block contains the pointer to the next block in the chain, and the file allocation needs just a single entry for each file and no external fragmentation to be worried about because each block is given according to the need of the file. So this is also best for sequential file, and this sequence of file can be collected into the file allocation table, and the allocation is given based on the need of the file size. The third approach is to have the index allocation with block portion. So how is it different from the previous method? So see here, okay, we have the block link that is chained together, but this time the chain is also part of the file structure. So inside the chain, there will be one block that contains the index of all the file block that needs to be consolidated and combined together in order to form a file. So for example, in the file allocation table, it will state that file B here is indexed at block number 24. So in block 24, there will be the information with regard to all the blocks that will be used to form the file. So inside the block 24, it says that, okay, we will need block 1, 8, 3, 14, and 28 to actually form the file. So this here, it contains the block of information inside a specified block that is also in the file system. So whenever it needs to reference or form back the file allocation table will just refer back to the index block. So let's say block 21 is for another file. So in block 21, it contains all the necessary information for all the other file also. The important thing is that the reference for the information that is needed to compile and build the file is contained in one single block that is called the index block. And lastly, we also have the index allocation with variable length portion. So how is it different from the previous one? So let's say you have also the index block from the previous method. So in this case, this combination of block can be of variable size and not just one single block. So for example, the index block 24 will indicate that, okay, let's say in order for the file to be formed, it has the starting block of block 1, but the length of the block is 3 blocks, while other information is we also need to use block 24 and 28, but the length is 4 blocks here. And we also need information from block 14, which contain only one block in size. So this is what it means by the variable length portion. So the index block is still there, but the combination of block is variety in size and not just one single block per allocation or per address. So here we have one block containing 3 size, one block containing 4 size, and one block containing only one size. This is what it means by the variable length portion. So in here, we still use the file allocation table, we still use the index block, but the combination of blocks has a variety in sizes. So this is the end for the file function and operation for this chapter. The thing that you need to remember from this chapter is why file is being used and what information can we gather from a file, what function can we do on a file, and what is the role responsibility of access rights with regard to file usage. Lastly, is the variety of file allocation method that can be used in the file allocation table. So, this is the final chapter of the operating system concept. So I hope it has been a very good journey for you with this chapter and subject, and I hope it can be very beneficial to you in your profession or in your life later on. So any question, feel free to ask me during the Q&A session. Thank you very much and have a great day.